Titan Z. So what can it do? What can the Titan Z do? Well, in order to talk about what it can do, I need to go back in history a little bit. 30 years ago, Pixar Animation Studios launched the world into full CGI animated feature films. Luxo Jr. 30 years ago was the first animation, CG animation, to win an Academy Award. RenderMan, with programmable shading, played a large role in inspiring us to build a GPU with programmable shaders in hardware. It took an hour and a half to render each one of these frames on a convex mini computer. And these scenes, notice they're beautiful. Programmable shading offered really soft lighting, specular highlights, proper lighting, shadows. Everything just looks natural and beautiful. Well, 30 years later, the work at Rhythm and Hues broke new ground. This is now 2013 Academy Awards Best Visual Effects. It's very, very clear now that generating a beautiful image is not enough. You have to first do the amazing physics simulations of the real world, so that you could create the mathematics behind water and fire and smoke and particles and collisions before you render it. The unification of simulation and computer graphics is very, very clear now, that computer graphics alone was not enough. The vision that helped us, that inspired CUDA for computer graphics, has really come true. Now, if you compare the work that Rhythm and Hues did, and this is really amazing, as fast as computers have advanced, in that short time, 30 years, computers advanced 1,000,000 times more powerful. And yet, what took an hour and a half to render per frame now takes 250 hours. The computer has become 1,000,000 times more powerful, and yet it takes 250 hours to render. Well, a lot of that time is consumed in just the physics simulation of the ocean. First, the base simulation, then particles, splashes, foams, all of that composited, merged together in some artistic way, and then, of course, rendering the final image. Well, just as we demonstrated Luxo Jr. at Macworld during the launch of the MacBook that NVIDIA was first in, and where the launch of the programmable shader, invention of the programmable shader, inside our company, the code name was MV20. That particular product launch, Macworld, we demonstrated Luxo Jr. in real time. The audience was just floored. Never has anybody seen beautiful graphics like that in real time. Well, ladies and gentlemen, we have a real treat for you today. Jim, let's go to the demo. So what we're doing here before we get started, we're in simulation and computer graphics at the same time. Now remember, first of all, what do you guys think, guys? Hey, how about let's do that one more time for them to enjoy it. Slightly different. Let's let them enjoy it one more time. And then we'll tell them about it. I think I got wet up here. So first of all, the wave simulation stirs up the plankton in the ocean, which created that iridescence. There's all jellyfish all swimming naturally all by themselves. When the whale comes breaching out of the water, it generates, of course, the waves. The wave simulation kicks in. They're 2D grids. They're 3D grids. They're particle systems. They're mist generators and foam generators. And all of that done in real time. And as it lands, the wake pushes the raft around. And not to mention, the computer graphics is just beautiful to look at. These guys did a great job. Thanks a lot, Jim. Now we'll show you a few more things. Next up, this is the world's first real-time unified physics solver. Fluids, cloth, rigid bodies, all interacting together in a unified solver. Every single physics detail is coupled. One physics simulation affects another, and all of the others around it. Okay, so all of the physical behaviors are coupled. The world's first unified physics solver in real time. So let's show them that.
Thanks, Jensen. So as Jensen said, this is what we call Flex. It's a fully unified solver where the fundamental building block is actually particles, and all kinds of different materials and different kinds of objects with different properties are represented using particles. So here we have, we're showing fluid interacting with rigid or solid objects.
And so, Jim, this is a turbulent flow simulation, and it's kind of like the turbulent flow, that vortices that come off the wingtip of a plane.
That's
and
right.
all the turbulent flow behind it.
Exactly. So the turbulent flow is generated depending on the actual interaction of the fluid with the solid surface, and so vortices are then generated, and that it leaves this beautiful wake.
And this is also the first simulator that is grid-free, right? For all of the computational mathematicians in the audience, there are no grids here, and it's grid-free, and so the simulation approach is a sparse matrix approach, which is really, really data movement intensive. Okay, let's see a few others.
Sure. Here's another scene which shows off the interactivity.
Let's go back to the last one, please.
Here's a scene which shows off the interactivity of different types of materials like we talked about. So here we have a rigid hanging material that we can then emit particles into the scene, and there's full interaction between that rigid body and the fluid smoke. So I can play with that, move it anywhere I want. I can stop emitting particles, emit some more fluid.
And so you could see that all of the physical simulations and behavior are all coupled. The smoke is interacting with that rigid body, and of course the springy rubber wires are interacting with everything as well.
Exactly.
Everything all very naturally. No artistic animation is necessary. You just set it free and let it simulate.
That's right. And because everything's represented as particles, they can all be efficiently simulated on the GPU. So this is all GPU simulated.
And so it takes something like a Titan Z, where we're doing the simulation on some of the GPUs, some of the CUDA cores, and of course the rendering, the computer graphics is also beautiful, is done by the other CUDA cores. Okay, let's take a look at another demo.
Sure, here's another nice scene which shows off both the beautiful fluid simulation and turbulence of this simulator, but also the ability for the actual the grid-free nature of the simulation. So typically we constrain simulations to grids because it makes it easier to simulate and bounds the problem in a way that fits nicely on GPUs. But this is the first time we've done a simulation that's completely grid-free.
Can you just imagine how naturally it is going to be for artists now to create video games and other content? The character would just show up, and of course there could be an explosion, or there just could be a layer of smoke, and they just walk right through it. And so no artist manipulation is necessary, and as a result, the cost of creating the content is reduced. But not only that, it's just much, much more beautiful and much more realistic. Okay, let's take a look at something that you just got a glimpse of. Fire is really beautiful. It's always something really cool to do. Of course, one of the things that we want to do is volumetric rendering. In this particular case, what we're doing here, we're simulating not pixels and grids, but we're simulating voxels. This screen that you're looking at is now split into 32 million voxels, which are basically little cubes in 3D space inside this simulation. Instead of a pixel, which is a dot, a voxel is a volumetric pixel, or a voxel, a cube. Each one of the cube contains information on the fuel, the amount of density, and the temperature. And if the temperature reaches a certain level, the fuel ignites. The fuel would ignite within that little tiny one of those 32 million voxels. And when the fuel ignites, it emits light. Okay, so what I'm describing here, once the engineers describe this scene and write this algorithm, the rest of it is just automatic. The rest of it just happens differently every single time. And so this is volumetric smoke and fire, and let's have some fun with it. Every single one of those voxels are interacting with that sphere, and as it comes close, it lights the sphere wonderfully. Look at the way that the flame and the smoke wraps around the sphere so naturally. The unification of simulation and computer graphics. Thanks a lot, Jen. Well, we've got to put it all together for you guys and always show you something you've probably never seen before. This is the work from an amazing company called Epic. This is their next generation game engine called Unreal Engine 4. Unreal Engine 4 is the first game engine that has integrated our GameWorks physics and computer graphics libraries. So the scene that you're about to see is completely generated in real time. Thanks a lot, Paul. It's generated in real time. You're going to see cloth simulators, water simulators. Look at the way that the environment is destroyed. The destruction looks real. It is real. It's simulated. It's not like a hole is painted on top of that wall. The wall actually got destroyed. Okay? So real simulation, real destruction, and not only that, really violent and really, really beautiful. Okay, let's run it. Ladies and gentlemen, Unreal Engine 4. That, by the way, is why we have to build Titan Z. Well, just to show you that it's in fact real time, the lighting makes such a huge difference in how this works. Lighting is one of the most computationally intensive part of computer graphics, and the ability for your eye to pick up those subtle lighting shades is really quite remarkable. So let's take a look at it real quick. This is flat lighting. This is without lighting. This is just basically texture maps. And this is essentially what computer graphics used to look like. Of course, you would just make the texture map a little browner or a little redder, but it's flat like that. In fact, if you take a look at most video games today on mobile devices and even on PCs, they tend to be flat-ish in the way that the lighting is done. Now turn on lighting, everything comes to life. And you add to it water simulators, particle simulators from the sparks, destruction simulators when the characters hit the wall, it just destroys all by itself because it knows how much force was applied to that wall, and as a result, it would destroy appropriately. Doesn't matter where you hit the wall, it would destroy it as appropriate. Simulation and visualization coming together. This is the future of computer graphics, and you're looking at it, getting a first glimpse of it here with Unreal Engine 4 running on Titan Z. Thanks a lot, guys.